And Asia will be speaking to us on partitions associated with the Ramanujan / Watson mop theta functions omega and nu.
Thank you. And first, I would like to thank Larry and Ian for inviting me to this wonderful conference. It's finally happening, and it's really great to be here. So today I'm going to talk about the Ramanujan and Watson mop theta functions, omega over Q and then the nu over Q. So my talk is based on joint work with George Andrews, Arthur Dixit, and then George. Okay, but the results I'm going to present today are a little bit somewhat old because we've so we completed our project several years ago, but I think the results are nice enough. So yeah, and then we will see how new ideas came around while we conduct this project. So let me start. We already saw the definition of a partition, integer partitions and then partition function. So let me start with the definition of mop theta functions. We already saw earlier in Amanda's talk, but anyway. So in 1920, Ramanujan introduced the notion of a mop theta function in his last letter to Hardy. And a mop theta function is a function of the complex variable Q defined by a Q series of a particular type. We call it Eulerian form, which converges for the absolute value of Q less than 1 and satisfies certain conditions. And then he listed certain conditions, but I didn't bother to put up on my slides. And this is the Ramanujan's definition of mop theta functions. And this is a little bit different from the modern definition of mop theta functions. Anyhow, then there are well-known mop theta conjectures formulated by George and then Frank Garban. So partition-theoretic interpretations of various results involving mop theta functions have been the subject of intense study for many decades, especially, as I mentioned, Andrews and Garban reduced the proofs of 10 identities for the fifth order mop theta functions from Ramanujan's law notebook to proving the two conjectures based on the rank of a partition and the number of partitions with some restrictions. Here, really unique smallest parts, etc. And these conjectures are known as mop theta functions and were first proved by Dean Hackerson in 1988. Okay, so as we saw in mop theta functions, some partition-theoretic interpretations play some important role. And here are some examples where the mop theta functions itself admits some simple and interesting combinatorial interpretation. So I'm gonna briefly mention chi over 1 and then chi sub 0 Q. Those are the 2/5 order mop theta functions of Ramanujan. And then Q times chi 1 over Q defined in this way. Okay, then from this, you can easily see this is a generating function for partitions in which parts are less than twice the smallest part. The reason is because here in the numerator we have a Q to the n, so n is the smallest part, and then in the denominator we can go up to only 2n minus 1, so the parts are less than twice the smallest part. And similarly, chi 0 Q given in this way, okay, then it can be also interpreted as the generating function for partitions, this time with the unique smallest part and the largest part almost twice the smallest part. Again, the numerator tells us what the smallest part, and then the denominator tells us what the other, the parts. Okay, and few other mop theta functions also have similar partition-theoretic interpretations. And these are the two of those few other examples. So first of all, this omega of q and the nu of q, these two Mach zeta functions are defined by Watson in his paper in 1936, but they also can be found in Ramanujan's Lost Notebook. Okay, so the combinatorial interpretation of these two third-order Mach zeta functions are easy, but I'm going to discuss that later of my talk. All right, then in 2015, George, Arthur, and then myself ran into another partition-theoretic interpretations that is related to omega of q, which I'm going to present. So the function p omega of n counts the number of partitions of n in which each odd part is less than twice the smallest part. Okay. So for example, let's consider the 11 partitions of 6. Okay, we saw 5 partitions of 4 already. So let's go with 11 partitions of 6. And these are the 11 partitions of 6. And the blue colored ones are the partitions counted by p sub omega of n. The reason is because, for example, look at 5 plus 1, the smallest part is 1, and the odd part must be less than 2 times the smallest. But here we have odd part 5, so 5 plus 1 is not counted by p omega. Okay, so altogether, there are 8 such partitions, and p omega of 11 is 8. All right, then the generating function p omega, from the definition, the conditions put on the part, the restrictions put on the parts, you can easily see that the generating function is indeed qn divided by this. Oh, maybe I missed one slide because I wanted to introduce this q pocket symbol notation, but we already saw in earlier talks, so let me just skip that. All right, so then that's it. And then the reason here in this denominator, q to the 2n plus 2, q squared infinite, tells us we don't allow odd parts that exceed, that are greater than twice the smallest part. That is the generating function. But surprisingly enough, this p omega has some connection to the third order Mach zeta function omega of q. Oh, here is the notation, sorry. Okay, so omega of q as the generating function p omega of n. Again, this was the third order Mach zeta function we saw earlier. Then 2015, okay, we saw that actually we were able to prove this identity. Okay, and the left-hand side, what we are looking at in the left-hand side is the generating function of p omega of n. So we have this relation. Okay. All right, then main ingredients in the proof. Okay, I'm not gonna go through the proof. I'm just telling you how we get such a nice Q-series identity. So there are 3 nice ingredients. The main ingredients. First of all, the George's 4-parameter Q-series identity. So this identity, he studied this identity to study partial theta functions in 80s. And then the next one is the Ramanujan's 1-psi-1 summation formula, transformation formula. And another one is this relation that links nu of q, one of the third order Mach zeta function we saw, and then omega of q. Okay. So combining this, all we need is, because we have this nice general 4-parameter Q-series identity, so we just specialize by choosing appropriate variables for b, a, and then little b, and then little a, and then use the Ramanujan's 1-psi-1 summation formula to convert one identity, one side into another one. That is the outline of the proof. So we are able to show that the first inequality follows just from the definition, and then the last equality using those formula, we are able to show actually that is equal to Q times omega of Q. Okay, and this is the way we get all the other results I'm going to present. All right, so then, so now we have a P omega, and then P omega, we got P omega by adding some additional conditions on the parts of ordinary partitions. Then here in this position, then we can go in various ways. First of all, we can generalize it by adding some extra variables to keep track of some additional nice statistics, for example, as we do with rank functions and crank functions. Or we can look at subset of partitions, like instead of just all partitions, we can look at partitions into distinct parts, or partitions into odd parts, or part partitions, or even over partitions. Okay, so let's first look at the partitions into distinct parts, and then throw in the same restriction, and then see what happens. And then surprisingly enough, okay, I'm going to tell it in a moment. All right, so this is the P nu of n. So all the conditions are the same, except we are looking at the subset. In other words, the parts are all distinct. Okay. All right. So for example, again, 11 partitions of 6, and then we saw that there were 8 partitions counted by P omega. Now this time we allow only distinct parts. Then of those 8, these are the 2 partitions counted by, the partitions with the same condition, but the parts are distinct. So 6 and then 4 plus 2. So here, P nu of 11 is 2. Okay, so we have a nice partition function, P nu counting function. Then the first step is, what is the generating function? All right. Then from the definition, we can easily see the generating function is the following. Because the parts have to be distinct, instead of 1 over something, we have this particle symbol. All right, and then one more thing I didn't mention was actually for the partition function, when we count P of n, we take P of 0 to be 1. Why? Because we count the empty partition of 0 as a partition. However, in this case, because the P omega of n matches Q times omega of Q, so we don't allow the empty partition as a partition in this game. So here again, the n starts from 1. All right. Okay. Then surprisingly enough, as you can tell, here the subscript is new, and then it has some connection with the Mach delta function nu of Q. So here, the third order Mach delta function nu of Q is this one. Then again, George and Arthur and myself were able to show that this infinite summation equals nu of actually negative Q. Okay. Then from this, we can easily show the generating function of P nu of n plus, because this generating function starts from n from 1, so the n equal to 0 case accounts for this middle one, negative q square sub infinity. The sum of this one equals actually mu of minus q. And then we know what this generates. This one generates partitions into distinct even parts. Okay. All right. And these are the further results. And how we got this theorem, as I showed earlier, use the Andrews 4-parameter generalization. This is a transformation identity. And then we had to choose appropriate values for the capital A, B, and then little a, and then B. And by taking some other variables and then also adding some other constructions, the conditions, we are able to get further results. So first of all, let's look at one by one. First of all, we take, instead of the odd parts, we put restrictions on even parts. And our partition set is the 4 partition set, the ordinary partitions. Then the generating function is Qn over this Park-Hammer symbol. Now here, we don't have any restriction on odd parts, so that's why we have 2 to the 2n plus 1 choose first of infinity appears. And this one relates some the sigma of Q, which was studied by George earlier in his paper on Ross notebook, and also plus some of these additional infinite series. Okay, and this time we can instead of just this time we put some restriction on unique smallest part. Why? Because in my first or second slide, we saw the difference between chi1 and then chi0 was the unique smallest part or non-unique smallest part. So we do that, then what we get is just merely what the partitions in statistic part. Okay, and then again we this time look at the small subset distinct parts and also add some restriction on even parts. Then we get this identity that involves another third order Markov function phi of Q. So here is phi of Q. Actually, yeah, this one is black. Yeah, okay, all right. And by adding some other conditions, we got further, by taking other combinations, we got further result, but they are not that nice enough, so I didn't put up on my slide. Okay, all right. Then, as I mentioned, taking in different subsets of partitions, we can go with a different partition subset of different partition sets, but also we can think of some Euler pentagonal number theorem type identities. So what is Euler's pentagonal number theorem? First of all, Dn counts the number of partitions of n distinct parts. Then the generating function is the following. Now this time we want to know the parity of the number of the parts. Okay, so dE of n it counts the number of partitions of n into an even number of distinct parts, and the dO of n count the number of partitions of n into an odd number of distinct parts. But then by changing the sign of this in the Park-Hammer symbol, minus to positive, so QQ sub infinity actually counts the generating function. Actually, that series is the generating function for this difference, dE of n minus dO of n. Okay, and we know this infinite series has a nice expansion, right? And this is called the Euler's pentagonal number theorem. And actually, if we expand this one infinite product, then there are lots of cancellations, and then only the coefficients of the series is either 0 or plus or minus 1. Okay, and then from this we can immediately tell that except for the numbers of capital N, partitions of this number n times 3 n minus 1 over 2 or plus minus 1 over 2, the number of the even partitions of n into even number of distinct parts matches the number of partitions of n into an odd number of distinct parts. Okay, so with P omega, we can think of a similar thing. So in other words, we want to keep track of the parity of the number of the distinct parts, number of parts. Okay, all right. And then surprisingly, this is what we got. So here, again, we assign a sign of to -1 to each part, which means whenever we have even number, the weight is +1, and then whenever we have an odd number of parts, the weight is -1. And so lots of cancellations, and then what we get is actually this Lachner series. So -1 to the j. So in other words, if the coefficients are either 0 or 1 or -1, and then 6j squared 4j plus 1, actually this is related to the Euler's pentagonal number as well. And the P nu case is about the same. Okay, so we keep track of the parity of the number of the parts. Then the generalization function tells us the number of the partitions counted by P nu with the even number of the parts, and then the partitions counted by P nu with the odd number of times are almost the same, okay, except for these numbers. All right. Okay, then looking at this nice now Euler's pentagonal number theorem type results, and also all the combinatorial interpretation of the P partitions counted by P omega and then P nu. The first question from a combinatorial point of view we can ask is there any nice kind of bijective proof we can connect one partition set to another partition set? Okay, so for that we need an interpretation of omega of Q, which I delayed to this point. So here is the Ferris diagram of partitions. It's not a usual Ferris diagram. Usually for Ferris diagram, we use just the dots or the boxes, but here we have two different types, the filled dots or the just circled one. And in microscope this morning, we talked about the hook length, right? So here we pick the Ferris diagram and then take the largest hook. So that is the hook of this top left one, circled one. And then take this, the first row, and then the first column. We don't fill them. This just leave it as like that. And then the rest, we just, those are the filled dots. And these two divided ones have two distinct weights. So the unfilled one has weight 1, and then the filled one has, each of the filled one has weight 2. In the usual Ferris diagram, each dot or circled dot or box counts just 1. However, in this case, weight 2 means for this dot, we assign weight 2. So we count this twice. Okay. And then nice thing about the Ferris diagram, we can define, Dolphy score statistic. So here is the largest score that fits inside the Ferris diagram, and then it divides the Ferris diagram into 3 different regions: Dolphy score, the sub-partition to the right of the Dolphy score, and then the sub-partition below of the Dolphy score, below the Dolphy score. Okay, so then what is the generating function for the partitions with this Dolphy score of this shape? Okay, then because of this, the largest Dolphy score, and then here, let's say the side is D, then the filled dots counted by 2. and then the circle ones counted by just 1. So we have 2d squared minus 2d plus 1 weight coming from this, coming out of this 30 square. And then the below, and then to the right, we have this 1 minus q squared, 1 minus q cubed, etc. Okay, why? Because these numbers, each rows and then each columns must be odd, right? And then what we know from our result, the p omega of n equals it has the connection with the omega of q. What we know is this is the generating function for the omega of, this is the third order Mach zeta function omega of q. And then we know this one equals p omega n q to the n. So this omega of q has nice combinatorial interpretation like this one. And then p omega, we defined p omega by adding some conditions on the odd parts. So the nice the combinatorial question we can ask, can we define bijection between one set like this one to another set of partitions counted by p omega of n. All right, that is that. And in an effort of proving, constructing such an bijection, George and I tried to, first of all, we had no clue at all at the time. So we first of all generalized the generating functions. What I mean by generalizing it is we throw in more variables. That means those variables keep track of, certain statistics. So we are looking at the smaller portion of the set we are looking at. So this is the two variable generalization. Okay. All right. So when z equals to 1, the left-hand side is exactly the generating function of p omega. And then the far right one, when z equals to 1, is q times omega of q. Okay. And then moreover, if we set z equals to -1, then we get just a two-line proof of the analog of Euler's pentagonal number theorem. Okay. Yeah, so if we can prove this identity, two variable generalization identity, combinatorially, then we can actually prove the bijection between the partitions generated by omega of q from the original definition, and then the partitions counted by p omega of n, and also the analog of Euler's pentagonal number theorem. But we were not able to do it, unfortunately. But I mean, it was done by other people, so I'm gonna present it in a moment. However, we have another two variable generalization for the p nu of n. Okay, so these are the okay. All right, but those generalizations are not, we are not the first one who considered those two generalizations. Actually, George, back in 1966, he considered the generalization of omega and then nu in this way in the study of basic hypergeometric series. And also, 2011, Yunsa Che, in his study of connecting some Mach zeta functions to basic bilateral series, hypergeometric series, he also considered this three variable generalization, omega tilde and then nu tilde. All right, and about 3 years ago, Lee and then Yang from Nankai in Tianjin, they studied these generalizations, and then they defined their own three variable generalization, omega, y, z, and then q. nu, y, z, and then q. But those are just the variation of the Yun-Chest generalization. Anyhow, they looked at this, and then they were able to show this omega yz is the following one, and then nu yz is the following one. However, they were not able to keep track of actually y and z, so that to find the three variable generalizations of the partition function p omega and then p nu. However, while analyzing their theorem, they actually were able to show that the construct of bijection between the partitions counted by p omega over q, p omega over n, and then the partitions with the Ferrous diagram with two different weights. Okay, all right. So what is their bijection? I'm not going to present it because it's really complicated. So if you're interested in, then at the end of my talk, I'll give you the reference. All right. Okay, then let's move on to some arithmetic, properties of the coefficient. Okay, p nu omega or a omega. What is a omega? That is the a omega of n is the coefficient of q to the n of omega of q. Okay, so a omega of n minus 1 is actually p omega of n. All right. Then the Sharon Garthwaite and David Penniston show that the following. So for any m such that the m is relatively prime to 6, then there are infinitely many arithmetic progressions. an plus b, none of which is contained in another, so that a omega an plus b is congruent to 0 mod n. Okay, so they got this result, I think, around in 2008. And then 3 years later, Matthias Walder proved the first explicit congruencies for a omega over n with the aid of Jeremy Lovejoy. So mod 5 p omega or 40n plus 28 congruent to 0, or a omega 40n plus 27 congruent to 0. And then, yeah. And so then because we in our project, we considered the p omega. So we looked at for further congruencies, and then 2019, Sellers, and then Passari, Tony Passari, George, and then myself found these explicit congruencies for mod 4 and mod A for p omega and then p omega. All right. Okay. And then here are some further congruencies. So Jan Brunier and then Ken Ono in 2011 got this congruencies, not exactly congruent 0 mod something. However, this a omega is congruent for any prime p greater than or equal to 5. So p 3 mod 5 12. So they went up to 5 12. If p is congruent to 1 3 mod a, otherwise this quantity. Okay, and at the end of their paper, they left a few remarks, and one of the interesting remarks is the following. They ask for any combinatorial explanation for the fact that for p congruent to 1 or 3 mod a, this a omega congruent plus minus 1 mod 5 12. Yeah. Of course, I don't have any. I don't know why I haven't looked at it. It's certainly interesting, but probably I guess it's hard because if we are looking for, instead of just identifying congruencies, we want real combinatorial interpretation or explanation or account, which means we have to find a nice statistic for example, rank and crank, right? And so I guess it is really hard. But at least, it has to be either 1 or -1. Okay, if P is congruent to 1 or 3 mod A, because N is mod 2 from the analog of Euler's pentagonal number theorem. Yeah, analogous, our analogous of Euler's pentagonal number theorem. But I don't know, I have no clue about this modulus 512 moment. Yeah, but I thought that some of you might be interested in this question. And also, Ernest Shia, 2018, he went up to mod 16, and then he showed that P omega of this number is congruent to 0 mod 16. So a lot of powers of mod 5, so mod 8 and then mod 16, or mod 4 and then mod 2, but except the Walters case, mod 5, we were not able to find any further congruencies. Okay.
So by the way, based on our conversation this week, we do have something in the open problem session.
Oh, okay. All right. Yeah. All right. Good. Okay, then as I said, we can. In the beginning, I said we may go in different directions, but here is the over partition analog. So an over partition is a partition in which the first occurrence of a part may be overlined. So as you see, 4 and 4 bar, we treat them as different partitions. Then over partition function p bar over n counts the number of over partitions of n, and then there are 14 over partitions of 4. All right, then we can define the analog or over partition analog of p omega or p nu in this way. So the difference is we have here on the top is extra, the product. The reason is because we are now overlying the parts. Okay, and then at the end of our paper, this one was doing work with George, Arthur, Dan, and then myself. And then at the end of our paper, put quite vague question. Can one say anything about modular behavior of this function? And then Brinkman, Jennings, Schaefer, and then Marburg in 2018, they showed that actually the generating function can be completed as a harmonic form, etc. And because of this extra factor in the numerator, the behavior is quite strange. All right, but it also has some congruencies mod 4 this, and then Fu and then Gao look for further. They found further congruence mod 4 like this one. Okay, and then now the analog of Euler's pentagonal number theorem for the overpartition case. We saw that earlier it was just one single Lechner series, but this time it's a little bit different, and then it's a Hecke type double series. So the structure, the function itself seems a little bit more complicated of that. And finally, we are here, the Andrews SPT function. And in the beginning, I didn't say the whole motivation of our project, but this was the starting point. What we wanted at the time, right after the Andrews SPT function, so many different SPT functions were studied, and then our project, the starting point of our motivation was do a little bit different SPT function. So what is Andrews SPT function? So in 2008, Andrews defined the smallest parts function SPT of n as the total number of appearances of the smallest parts in all of the partitions of n. So for example, we know there are 5 partitions of 4, but there I underline the smallest part in each partition. So there, and then we count the underlined part in the whole partition, so 4. Then there are 10 underlined parts, so SPT of 4 is 10. And then Andrews proved the 3 surprising congruences for SPT of n, mod 5, 7, and then 13, not 11 this time. Anyhow, SPT function possesses very similar and then nice arithmetic properties as the partition function P of n. All right, and then this is a generating function. I think I'm kind of so let me just skip this because I think some of. So what is what is the generating function for SPT of n? This is a generating function, and then the difference is here we have at the bottom, not the bottom, denominator 1 minus q to the n square, and then this square factor actually enables us to keep track of how many smallest parts occur throughout all the partitions of n. Okay, and then Andrews proved SPT of n is related to partition function, and then Atkin and Garban second rank moment n2 of n, and then using this identity, he was able to prove all the SPT congruencies. So we can then define a similar SPT function on the subset of the partitions counted by P omega or P mu. So SPT omega of n count the number of smallest parts in the partitions enumerated by P omega of n. So these are the 8 partitions of 6 enumerated by P omega, and then I underline the smallest part, and then there are 21 smallest parts altogether. All right, and this let me make a remark. This smallest parts function actually was also studied by Garban and then Jennings Schaefer in their study of smallest part functions arising from different Bailey pairs. Okay, then what is the generating function for SPT omega? That is this one. So the only difference is in the numerator, denominator, we have this score thing to keep track of the number of the smallest parts. And what we get out of this, actually we need another nice expression for this SPT omega of n. To get to that, we need Bailey's 10p9 transformation. In the original proof of SPT of George, what we did is took the Watson's AP7. Now we go one higher up. We looked at Bailey's 10p9. That was our whole motivation, looking at one above and then do the same thing and then see what happens. So this is what we get. If we do that, then the generative function SPT of sub omega of n is this one, but also from the Bailey's 10p9, what you get on the other side is this expression. Oops. Yeah, it's this expression, this one, right? And then from this, now we have nice order form, and then product, and then the second rank moment. Then using all the information out of this, we can get this some congruencies for SPT omega. Okay, so we were able to find only mod 5, so SPT omega 5 n plus 3 congruent to 0 mod 5, etc. And we can go with similar analog for over partition SPT omega of n. So here is the generating function, and then we also were able to find the congruence, mod 3 congruence for the over partition SPT omega 3 and congruence 0. Actually, this is these two results are very similar to the SPT, just over partition SPT congruences without omega proved by Lovejoy. Okay. Yeah, I think I have to check either Lovejoy or Christian Schaefer. Sorry about that. My memory is yeah at the moment. So either one of them. Okay, and then the the same game for the new SPT new win. Then we are also able to get SPT new 10n plus 8 congruent 0 mod 5. So one more thing I want to mention is in this case, SPT new is the same as P new. The reason is because the parts are all distinct. So the smallest part, there is only one. Yeah, so it's nothing new. All right. And to close, these are the references I used to prepare my talk. And then, yes, this is the paper I mentioned, frankly, and then Jane Yang about the combinatorial proofs for the identities for the omega of Q and then the P omega. And then, yeah. So then, I think that's all I wanted to say today. So thank you so much.
Any questions?
So in the beginning of your talk, you mentioned these new interesting combinatorial computations for omega and nu. Do you get any results in these directions for other quantitative functions, or?
Yeah, that is a good question. And then actually, when we submitted this paper, one of the referees pointed out to research, search more. And I think we thought about it, but we didn't actually work hard. So it is still open. My answer is, I don't know if there is a nice incidence like this one exists for other multiple functions. But if there exists, it would be nice. Yeah.
For the T function, you had something similar, but it's
right.
Sort of more complicated.
Yes.
That function is related via one of these theta.
Right.
Conjectures.
Yeah. So by adding different conditions, we got three third order Mach theta functions here and then there. So I think at the time we looked for the fifth order Mach theta function, but we didn't work that hard. So yeah, my answer is still I don't know.
You have any questions? No, not enough. Okay. Robert, you have a question?
The funny thing is I do, but I don't know if anyway.
I thought you were starting to.
Oh, yes, okay, great, very observant. So it was just a quick one. I'm not sure, part of the reason, I wasn't sure how to phrase it exactly, but for some identities that kind of vaguely reminded me of these, there have been like these lead theoretic methods, like using affine Kac-Moody algebras to derive some of these Rogers-Ramanujan identities. There's a whole framework for that, and I think also some Andrews-Gordon identities. So
yes.
I was just curious if there's any connection or anyone's tried those kinds of ideas with these sorts of identities?
I don't know. Yeah, my answer is I don't know. So the Rogers-Ramanujan and Rogers-Ramanujan-Gordon, we have a nice theoretical background, from algebra, right? But for those, I don't know.
Well, I think they'll be interested in stuff next.
Okay.
Any other questions?
Yeah. So I guess a lot of the congruences that you displayed were powers of 2.
Yes.
Which, I guess this is maybe some of what's going to be in the problem session, but
are easy ones.
Is there any like maybe experimental evidence for
Mhm.
something like for arbitrarily high powers of 2? Like
But
keep it
yeah,
like
we
a
got
operator?
some high powers from some data, but we were not able to actually prove it. So we didn't. I don't know. I mean, we revised our paper over and over. So at first, yeah, let's include it as open questions, and then later, just exclude it for later, and then we didn't get back to that. So. But I will, for that, I will have to dig up my emails. Yeah, so, but we got some data for higher. Those are not the only ones. Those are the ones we were actually able to.
And I can say from the other perspective, from the Borges product perspective, when Ken and Bruni were doing that, and that's why I wanted to also put in the problem session, because the paper is 10 years old, and I don't think it's been cited too much. But it's an interesting modular method. I remember Ken saying at the time that 512 is just where they stopped. That Ken had the impression you could maybe even keep going for even higher powers. It's more and more difficult in a bigger and bigger sort of space. And there's nothing special about it. It's just as far as they were willing to go to work.
Just a small observation about this. I know that Li Kuan Wang, Yi Fan Yang have found an infinite with SBT omega for powers 5.
Yeah.
So I would not be surprised if there were some powers.
Something out there, but right, yeah, there should be. So, more to explore.
Thanks for pointing out. I wasn't be interested in that.
Yeah, it's they did a proof using the Peter and Solis techniques,
Mhm.
and I'll mention it tomorrow. Oh, great.
No, let's thank Asia again. And the talk will resume in 5 minutes. It will be a virtual talk. Let's